Hi everyone, and welcome to our first video for the quarter. So before I get into the actual content of this video, I just wanted to mention a couple of tips that I have for how to approach watching the videos for this class. So the videos for this class are going to have a combination of introducing concepts and explaining why those concepts work the way they do, as well as a lot of examples. And so what I would recommend doing when you're watching these videos is to as soon as you feel kind of comfortable with a concept, to pause the video and try the examples yourself. So sometimes I'll explicitly tell you in the video, I want you to pause it and try this example yourself. Other times I won't actually say that out loud, but just know that that's always an option. And the reason that I recommend doing that is that otherwise watching this video would be a very passive experience. And I think it's going to be a lot more engaging and you're going to get a lot more out of it if you are actually trying the examples as we go. And it will also allow you to maybe get through the video a little bit more quickly, because if you try an example and you get the answer, you don't have to watch my entire explanation. And then, if you don't get the right answer, then you can watch the explanation. And I think the explanation will be a little bit more meaningful if you've actually tried the problem yourself. So I highly recommend approaching the video that way. The other thing I wanted to mention is that there are lecture notes posted for each video. So if you go on Canvas and look at the link for the video, you'll see lecture notes posted right below. So the lecture notes are just exactly what I'm writing on the screen here. I know a lot of students find that taking their own notes is very helpful to their learning. So you're definitely welcome to take your own notes, but if you do find it useful, you can always refer to the lecture notes. I will say that, in the videos, there's going to be some stuff that I say out loud that does not make it into the lecture notes. So I think that the lecture notes just by themselves are not the same as watching the video. So I wouldn't try to just read the lecture notes in order to skip watching the video. Other last thing I want to mention is that for every video, there's a worksheet that is meant to go with the video to help you practice the concepts that we learned in the video. And sometimes I'll put problems that go a little bit beyond what was covered in the video to kind of look forward to the next topic or something like that. So that is also on Canvas. Under the link for each video, you'll find a worksheet. Okay, so let's get into our topic for today, which is antiderivatives. So this is something that you are supposed to learn in Calculus 1. So I think for most of you, the content of this video is going to be review. But we'll see later on in the quarter that antiderivatives are actually a really, really big part of the content of this class. So we're kind of going over them at the beginning of the class, then we'll get into some other stuff, and then later we'll kind of come back to antiderivatives. So what is an antiderivative? It's basically going backwards. So, in Calculus 1, you're usually given a function and you're asked to find the derivative of that function. And so antiderivative basically means going backwards. So you're given the derivative and you need to figure out what the original function was. So here I wrote down an example question that involves finding an antiderivative. And so I'd recommend that you pause the video and think about this question. So if you're given a derivative, if you're told that the derivative is the function 2x, f prime of x is equal to 2x, what can you say about the original function? So I would ask you to see if you can come up with, one possibility for what f of x was, but then see if you could come up with even more than just one possibility. Is there more than one function that f of x could have been? So the first function that you probably came up with, or at least what I would come up with first, would just be f of x is equal to x squared, right? So that would be a function that would work because when you take the derivative of x squared using the power rule, you would get 2x. So that is one possible answer. However, that is not the only possible original function. So I'm going to write down another possibility. You could also have x squared plus 1. So why would that also work as an option? Well, when you take the derivative, if you remember from Calculus 1, when you take the derivative of a constant, so this plus 1 part, its derivative is just 0. And so the derivative of x squared plus 1 would still be 2x. I'll write down one third option just to really emphasize this. You could also have something like x squared minus 100, right? Because when you take the derivative of negative 100, that's 0. And so you'd still just get 2x as your derivative. So these are all examples. All of these functions are examples of antiderivatives. So these are all examples of antiderivatives of the function f prime of x is equal to 2x. So that's what I mean by working backwards. When you're given the derivative and you're working backwards, the function that you're finding is what's called an antiderivative. So, these are each their own individual specific function, but when we're talking about antiderivatives, because when you take the derivative of a constant, you always get 0, you could really tag on any constant you want, right? We could have had f of x minus negative 3.752, we could have x squared plus 3,000. You could tag on any constant you want, and the derivative of that constant would still be 0, so the derivative of the whole function would still be 2x. And so the way that we kind of lump all of those possibilities together is by writing plus c. So we can summarize all these different possibilities. We only wrote down 3 of them, but there's infinitely many because you could add any number at the end as f of x is equal to x squared plus c. And so c here represents any constant. So a constant is just another way of basically saying a number, right? So c here represents any number. It could be 5, it could be 7, it could be pi, it could be negative 12, any constant. And so when you write down an antiderivative like this, where you include the plus c, this is what's referred to as the general antiderivative. And so later in this video, we'll get into finding specific antiderivatives. But a general antiderivative just means that you're acknowledging the fact that you don't know what constant could have been there, right? Because if the only information that you're given is the derivative, you just don't know whether there was a number being added to it or not. And so you say plus c to be as general, as inclusive as possible when you're expressing your antiderivative. Okay, so let's talk about some kind of general vocabulary and notation. So in this example, we were given the derivative using the notation f prime of x, right? We were told f prime of x is equal to 2x, and so what we found was f of x. So I'm going to focus on kind of the right side of this diagram that I'm writing down. So what's going on here is that if you're going from f of x to f prime of x, you're taking the derivative, right? So in this direction, what you're doing is taking the derivative. If instead you're going from f prime of x to f of x, the relationship is that it's the antiderivative. So sometimes, instead of being given f prime of x as the derivative, you're given just f of x. You're told f of x is equal to this, find its antiderivative. And so how do you kind of express the antiderivative of f of x? Well, you just use a capital F. And so if you're taking the antiderivative of f of x, little f of x, you use a capital F. And if you're a little confused about what's going on with this notation, I think throughout this video we'll see plenty of examples and it will become clear. It's just a convention. Typically, if you're given f prime of x, the antiderivative you write as f of x. If you're given f of x, you write the antiderivative as capital F of x. And so if you take the derivative of capital F of x, that would give you little f of x. Someone once asked me, what if you want to take the antiderivative of capital F of x? And someone jokingly was like, well, do you just keep making the f get bigger and bigger and bigger? And generally that's not going to happen, but you could always use a different letter, right? You could say, well, I'm going to let g of x represent the antiderivative of capital F. So what I wrote down here is just the typical convention, but you can always use a different letter as long as you kind of make it clear that you're talking about the antiderivative. Okay, so let's look at some examples. And we're going to try to come up with a kind of general rule to allow us to take certain types of antiderivatives. So I'd recommend you to pause the video at this point and try out finding the antiderivatives of f of x is equal to x squared and g of x is equal to x cubed. So again, we're not finding the derivative, we're finding the antiderivative. We're trying to figure out what would be the function that when you take its derivative, you get x squared, and then what would be the function that when you take its derivative, you get x cubed. So pause the video, play around with this a little bit, and then come back. Okay, so let's start with x squared. Okay, so what do we know about taking derivatives? Well, we know that when you take the derivative of x to a power, you subtract 1 from the exponent, right? And so what would need to be the exponent on our original function? Well, it would need to be x cubed, right? So because our original function is written as little f of x, I'm going to write the antiderivative as capital F of x. That's what we talked about on the last page. And so we know that it has to be x cubed, right? That's the only way that when you take the derivative, you can end up with x squared. However, if we take the derivative of x cubed, so let's say we're just taking the derivative of just x cubed on its own, we would get 3x squared. And that's not our original function, right? Our original function is x squared. So how can we kind of compensate for the fact that we have this 3? Well, we can take the reciprocal of 3 and put that as our coefficient on the antiderivative. So if we make our antiderivative 1/3 times x cubed, well, then that's going to work. And I'll show you how it works in a second. There's one thing that we're missing, right? We're missing a plus c because we're trying to find the most general antiderivative. So one thing I want to point out that I think is maybe even the most important fact from this video, you can always check your work. When you're finding an antiderivative, you can always check your answer because you know how to take a derivative, right? That's what you learned in Calculus 1. So anytime you're trying to come up with an antiderivative, I would highly recommend that you check it by taking the derivative. Not only will that help you make sure you get the right answer, but I think it will also give you some insight as to why these antiderivatives work the way they do. So let's check this one actually. So if we check this one, how do we check it? Well, we just take the derivative, right? And we want to ensure that we get the same answer as our original function. So how do you take the derivative of 1/3 times x cubed? Well, you have 1/3 times, so remember when you take a derivative, the coefficient just kind of gets carried along. And then you would bring down the 3, so you would have 3x squared. And so what happens when you multiply 1/3 times 3x squared? You get x squared, and that's exactly what we wanted for our original function. Okay, so now that we see how this works, we'll see that finding the derivative, or sorry, the antiderivative of x cubed is going to follow a very similar pattern. Okay, so let's use capital G to represent our antiderivative. So similarly to the last one, we know that if we're trying to take a derivative and get x cubed, that tells us that our exponent would need to be x to the 4th, right? That's the only way that we're going to get an x cubed when we take the derivative. But when you take the derivative of x to the 4th, the 4 is going to come down, right? And you're going to have 4x cubed. And we don't want that. We just want x cubed. And so how do we compensate for that 4 that would be coming down? Well, we can multiply with 1/4. So let's check this one as well. So if we take the derivative of g of x, capital G of x, we would get 1/4 times 4x cubed. And what happens when we multiply together 1/4 and 4? Well, that becomes 1, and so we're just left with x cubed, which is exactly what we wanted. So this general pattern is actually going to work. And actually, I forgot something. So what did I forget? I forgot to put plus c. It's very easy to forget the plus c, but don't do it, right? If we're talking about the general antiderivative, you need to write plus c, or else you're actually just writing down one specific antiderivative rather than the most general one. But yeah, so this rule is going to work in general. So notice what the pattern is here. If we look at the exponent in our original function, and then we compare that to the exponent in the antiderivative, the one in the antiderivative is 1 bigger. And that's just because of how the power rule works when you take derivatives. So similarly here we have 3 and then we have 4. And then what is the coefficient going to be? Well, the coefficient is always going to be the reciprocal of that new exponent because it needs to cancel out with the exponent when it gets brought down using the power rule. Okay, so what can we say our general rule is? Well, the antiderivative of f of x is equal to x to the n is going to be capital F of x is equal to, so we know that the new exponent is going to be n plus 1, right? It's going to be 1 bigger than the original exponent. And then what is this coefficient going to be? Well, it's going to be 1 over whatever the new exponent is, right? 1 over, so for example, here we had 1 over 4 x to the fourth. Same thing here. Whatever n plus 1 is, we have 1 over that. So this is a really, really important rule to know. This is like, so when you learn, in calculus, you learn all these different derivative rules, and one of them is the power rule, right? And so this is what's called, or what you can think of as being the reverse of the power rule. There's one kind of restriction I need to add to this, and we'll see why this is in a few minutes. This is only true when n is not equal to -1. So thinking about your original function, your original function is x to some power, so it could be x squared, it could be x cubed, it could be x to the 10th, it could be x to the -4, it could be x to the 3/2. It just can't be x to the -1. If it's x to the -1, this antiderivative rule is not going to work, and we'll see a different antiderivative rule in a moment. And I forgot again the plus c, so let me write that down. Plus c. And let me just add in this note. This is for all n not equal to -1. Okay, so let's see how this works in some examples. So for example, if our original function is f of x is equal to x to the 100, well, that means that the antiderivative is going to be, so I like to start by first finding the new exponent. So the new exponent is going to be the original exponent plus 1, so that's 101. And then the coefficient is just going to be 1 over 101. And then we have plus c. So if you took the derivative of this, you would get 1 times x to the 100, which is what our original function is. Okay, so next example is one that maybe doesn't look like the examples that we've done previously, but if you have the square root of x, that can be written as x to the 1/2. Right? So one thing I want to be really clear about is right now I didn't take any antiderivative or derivative or anything yet. All I'm doing is just rewriting square root of x as x to the 1/2, right? It's just a different way of writing the same function. But now that we have it written like this, now we can apply the reverse power rule. So we can say our function is capital G of x is equal to, so again, especially when the exponents are fractions, I think it's much easier if you start by finding the new exponent and then figure out what the coefficient is. So the new exponent is going to be 1 plus 1/2, right? And so what is 1 plus 1/2? That's going to be 3/2. I'll make a note of where that came from. So you're always just taking the original exponent and adding 1 to it. So 1/2 plus 1 would give us 3/2. So what is the coefficient going to be? Well, you could write it as 1 over 3/2, but I think the nicer way to think about it is that it's always going to be the reciprocal of the new exponent. So what's the reciprocal of 3/2? Well, it's 2/3 plus c. So let me make a note of that as well. So this is the reciprocal of 3/2. So you could write 1 over 3 over 2, but if you simplified that, you would just get 2/3. So I'm going to add a note to this because I think that's really the best way to think about it, is that this number is always going to be the reciprocal of n plus 1. So if n plus 1 is, 5, it would be 1 over 5, but if n plus 1 is a fraction, then you can just take the reciprocal of that fraction. Okay, one more example. So here we have 1 over x squared. So again, initially this doesn't look like it kind of fits the right format, but we can rewrite this as x to a power, right? So 1 over x squared is the same as x to the -2. And so once we have it written as x to a power, then we can just apply the reverse power rule. So here we would have capital H of x is equal to, so let's start by finding the new exponent. So the new exponent would be -2 plus 1, right? And so what is negative 2 plus 1? That's negative 1. So let me make a note of where this came from. This was negative 2 plus 1. So we just took the original exponent, added 1 to it. And then what is the coefficient going to be? Well, again, it's always just the reciprocal of your new exponent. So what's the reciprocal of negative 1? It's still negative 1, right? 1 over negative 1 is still negative 1. And so we can write this as negative 1 times x to the negative 1. And a nicer way of writing this would be negative 1 over x, right? X to the negative 1 is 1 over x. So we have negative 1 over x plus c. So that's how the reverse power rule works. And we'll see some more examples later in this video as well. So next, I want to talk about that issue of what happens when x, or when that power is equal to negative 1, right? So we said that this rule that we put in this box, it does not work when your exponent on your original function is negative 1. It does not work for x to the negative 1. So why is that? So what would be like a nicer way of writing x to the negative 1? Well, x to the negative 1 is equal to 1 over x, right? Just a different way of writing the same thing. So what is the antiderivative of 1 over x? So maybe pause the video and think if you can go back to what you know about derivatives and think about what is the function that when you take its derivative, you get 1 over x. So the function that when you take its derivative, you get 1 over x is ln of x, right? ln of x, the derivative of ln of x is 1 over x. So there's one small change that we have to make. We can't just write down ln of x. We actually have to write ln of absolute value of x. So why do we write ln of absolute value of x? So basically, remember that you can only take, if you go back to when you first learned about logarithms, you can only take a logarithm of a number that is greater than 0, right? You can't take a logarithm of a negative number. It just doesn't make sense. The domain of a logarithm is all numbers greater than 0. And so the issue is that when you're given the function 1 over x, x could have been negative, right? You don't know if you have the function f of x is equal to 1 over x, x could have been negative, x could have been positive. There's all these different values of x. So you want to make sure that when you take the antiderivative, that it's an actually defined function. And so in order to guarantee that the antiderivative is defined for all values of x, we have to add this absolute value, because the absolute value ensures that you're not ending up taking a logarithm of a negative number. So let me make a quick note of that. So this is basically just the absolute value is there to ensure or to guarantee that you're taking ln of a number that's not negative. And so another way of saying that is you want to guarantee that ln is defined, right? ln of a negative number would be undefined. And so by forcing the input to be non-negative, you're guaranteeing that this function is actually defined. So basically 2 different rules. If you have x to the negative 1, the antiderivative is just ln of absolute value of x. If you have x to any other power, so could be a huge number, a tiny number, a negative number, a fractional number, in every other case, you can use this rule. It's just when x is to the negative 1 that you can't. Okay, so let's do another couple examples practicing with what we just learned. So in this example, we want to find the general antiderivative of g of x is equal to 3 over x plus 7x squared minus square root of x plus 5. So if you feel like you have a good handle on this, feel free to pause the video and try this yourself. If not, feel free to watch along. So one thing about antiderivatives that's important to know is just like with derivatives, you can split it up with addition. So every term you can take the antiderivative of individually and then just kind of add them together, because that's how derivatives work too. And then same thing when you have a number being multiplied, you can just kind of take that to the side and focus on taking the antiderivative of the rest of it. So I'm going to rewrite this a different way that will help us to kind of more easily take the antiderivative. So 3 over x, that's the same thing as 3 times x to the negative 1. Or you could write it as 3 times 1 over x. That part doesn't really matter. because we know that, right, for x to the -1, we're not going to use the reverse power rule. We're going to use the ln derivative. Okay, so we have 3x to the -1 plus 7 times x squared. Then we have minus square root of x. So square root of x can also be written as x to the 1/2. And then we have plus 5. Okay, so let's take our antiderivative. So the antiderivative, we can go through term by term. And so this 3 is just going to hang around the same way it does when you take a derivative. So the antiderivative of x to the -1 is ln of absolute value of x. And then, okay, what about this next part? So we have 7. 7 is going to get multiplied with whatever our antiderivative is. And then we can focus on finding the antiderivative of x squared. So the antiderivative of x squared, we saw that one already. That's x cubed times 1/3. Okay, and then here we have minus x to the 1/2. And so what is our antiderivative here? Well, we make our new exponent. We already did this one earlier, actually. So we got 3/2 for the new exponent by adding 1. And then we take the reciprocal of 3/2, and that gives us 2/3. Okay, then what about 5? So remember, we're not taking the derivative, we're taking the antiderivative. So what would be the function whose derivative is 5? You know, can you think of a function that when you take the derivative, you get 5? Well, that would be 5 times x. Right? The antiderivative of 1 is x, because when you take the derivative of x, you get 1. And so the derivative, or the antiderivative of 5 would be 5 times x. And then we have plus c, right? Because we're finding the most general antiderivative. So let's clean this up a little bit. So this would be g of x is equal to 3 times ln of absolute value of x plus 7/3 times x cubed minus 2/3 times x to the 3/2 plus 5x plus c. And I would encourage you to check your answer by finding the derivative of this. So if you find the derivative of this, you should find that you get back to your original function g of x. Okay, so let's look at one that is going to have kind of one extra step. So it says find the general antiderivative of, and we have a function that now has a numerator and a denominator. So one thing I want to make clear is that you cannot take the antiderivative by taking the antiderivative of the numerator and the denominator separately. So remember that in calculus, when you're taking the derivative of a quotient, you have to use the quotient rule, right? You can't just take the derivative of the top, derivative of the bottom, divide them. It just does not work that way. And so similarly, when you're finding an antiderivative, you can't just take the antiderivative of the numerator and denominator separately. So it turns out there actually isn't really a reverse quotient rule. So we'll see all sorts of different methods for dealing with functions that involve a quotient. But in this case, the best approach is to start by simplifying our function. So how can we go about simplifying this function? Well, it's a fraction with 2 terms in the numerator, and so we can split it up into 2 fractions, right? We can rewrite it as -3 times the square root of x over 4x plus x cubed over 4x. So I just want to pause for a moment and say that this is a really, really important trick to be aware of. I think, most people are used to seeing 2 fractions like this and adding them together to get a fraction like that, but it's important to realize you can also go the other way. You can also take a fraction and split it up, as long as you just have 2 different terms in the numerator, and then you leave the denominator the same. So why is this useful? Well, now what we're going to be able to do is we're going to be able to simplify each of these 2 fractions, and we'll be able to use the reverse power rule on both of them. So let's rewrite this slightly differently to help us. So 3 times the square root of x, we can also write that as 3 times x to the 1/2. And then we still have x cubed over 4x. So again, just to be clear, we have not taken any antiderivatives yet, right? All we're doing is we're just rewriting our function a slightly nicer way. So, and actually, let me just move this up because I think I might run out of space. Okay, so how can we simplify each of these? Well, remember that when you're dividing numbers to a power, you can subtract your exponents. And so we can rewrite this first one as -3/4 times x to the negative 1/2, right? Because if you were to do 1/2 minus 1, subtracting your exponents, you would get negative 1/2. And then for this next part, we would have 1/4, and then we have x cubed over x, and so that's x squared. So again, this is still our original function. We have not done any calculus yet. We're just doing algebraic simplification. But now we're ready to find the antiderivative, right? Because now we have it in a format where it's just x to a power, x to a power. And so our first one, we take our coefficient and just kind of leave that, that's just coming along for the ride. And then we can find our new exponent. So how do we find the new exponent? Well, we add 1 to the original exponent. So negative 1/2 plus 1 is positive 1/2. And then our new coefficient is going to be the reciprocal of that number. So that's going to be 2. 2 over 1, which is just 2. And then over here we have 1/4. And then we have x squared. And so we know that that's going to be x cubed. And then the reciprocal of 3 is 1/3. And then we have plus c. And then we can simplify this, right? And that will give us our final answer. So our final answer is going to be negative 3/4 times 2. That's negative 3/2, x to the 1/2. And then here we have plus 1 over 12, x cubed, plus c. So that would be our antiderivative. Let me actually change the color of this one so that it doesn't blend in to that one so much. Okay, so our next question is asking us to find another general antiderivative. So the way that this one is different is now we're going to see some functions that do not use the reverse power rule. So these are going to be functions where you just have to kind of remember some derivative rules from calculus. Okay, so remember that, again, we are trying to figure out what would be the function that when you take its derivative, you get this function. So we can go through term by term and just focus on each piece individually. So what would be, we can put the 5 here and we can just focus on this cosine. So what would be the function that when you take its derivative, you get cosine? Well, that would be sine, right? The derivative of sine of x is cosine of x. So the antiderivative of cosine of x is sine of x. Okay, then here we have something divided by 2, and so that means we have a coefficient of 1/2, so we can bring that along. And then what would be the function that when you take its derivative, you get secant squared? Well, that would be tangent, right? The derivative of tangent is secant squared. Okay, next we have e to the x. So what is the function that when you take its derivative, you get e to the x? Well, this one is just e to the x, right? The derivative of e to the x is e to the x, and therefore the antiderivative of e to the x is e to the x. Okay, last piece. So 1 over 1 plus x squared. So this is one that, probably I think less people remember, but this is actually going to come up quite a bit in calculus 2. So the function whose derivative is 1 over 1 plus x squared, that would be inverse tangent, or sometimes you write it as arctangent. So inverse tangent of x. And then we just say plus c. So this one was pretty different from the previous ones, right? We didn't really have to do any, adding of new numbers and taking the reciprocal because none of these were powers of x, right? These are all different types of functions. And really the main issue here is just to remember your derivative rules. So it's really important that you know your derivative rules from calculus, basically. Okay, so so far in this video, we've been talking about finding general antiderivatives. Right? So we've had this whole plus c business. So the first example that we started with in this video was we had if our original function is equal to 2x, then we know that the antiderivative would be x squared plus c. Right? That is what's called a general antiderivative. And I just want to give you kind of a visual to think about what general antiderivatives mean. So here I have graphed the function x squared plus c, and so I have c set to be a slider, meaning that I can vary the different values of c, right? And so our most general antiderivative is going to be x squared plus or minus any number you want to add on. So one thing I just want to point out is that if you remember like what derivatives really mean, derivatives tell you about the slopes of the tangent lines to your graph, right? That's what the derivative means. And so if you think about it, if you have this parabola and you're just adding or subtracting different numbers from it, it always has the same shape, right? So all of these different functions that I'm tracing out by moving c, they all have the same derivative, right? Because if you were to measure the slopes of the tangent lines, they would be the same. The slopes of the tangent lines do not depend on, where this parabola is sitting. They just depend on the shape of the parabola, and the shape does not change when you just add a constant. So that's another way of thinking about why this plus c thing exists. So in some cases, you're going to want to know not just the most general antiderivative, but one specific one. So how would this work? Well, you have to be given a little bit more information. So let's say that we're looking back at this same first example. So you're given that the function f of x is equal to 2x. But let's say we're given a little bit more information. We're also told that for our antiderivative, if you plug 1 into the antiderivative, you get 12. So this gives us a little bit of additional information that will allow us to figure out specifically what our antiderivative is without having to just say plus c. So how can we do this? Well, basically, we can first start by writing down the most general antiderivative, right? So f of x is equal to x squared plus c. But now that we know that f of 1 is equal to 12, we can use that information to figure out what c is, right? So if we plug f of 1, if we plug 1 into this function, we would get 1 plus c. And according to the information we're given, we're told that 1 plus c is equal to 12. And so what does this tell us about c? It tells us that c has to be equal to 11. And so in this case, we can be a little bit more specific, right? We can say that our antiderivative is not just, x squared plus any number, it's specifically x squared plus 11. And so what's going on here, kind of going back to this graph that we were looking at, is originally we were saying that our antiderivative could be any parabola like this, shifted anywhere. But now that we're given the extra information that f of 1 is equal to 12, that's giving us a specific point that must lie on the graph of the antiderivative. So if I set c equal to 11, sorry, it won't let me do it on the slider, so let me just put that there. So if I set c equal to 11, well, now we can see that this antiderivative goes through the point 1, 12, right? Which fits with what we were given. We're given that f of 1 is equal to 12. And so by being given that extra information, that specific point, that pins down the specific antiderivative that we're looking at, rather than just being like, what are all the possible antiderivatives? So let's look at a couple of examples that kind of fall under that, that category. So in this example, we're given a function, f of x is equal to 2 times e to the x minus 3x squared plus square root of x plus sine of x. And then we're also given the information that f of 0 is equal to 5. And so we're supposed to find our antiderivative, a specific antiderivative. So first thing we want to do is find the general antiderivative. So we always start by doing that first. Okay, so what is the antiderivative of 2 times e to the x? Well, it's just 2 times e to the x, right? The derivative of 2 times e to the x is 2 times e to the x, so vice versa is true as well. Okay, what about minus 3 times x squared? Well, you could write this as negative 3 times and then figure out the antiderivative of x squared, right? The antiderivative of x squared we've seen before is 1/3 times x cubed. But notice what's going to happen is that this 3 and this 1/3 are actually going to cancel out. And so, it might be nice to just recognize right off the bat that the antiderivative of this is just x cubed, right? Because the derivative of x cubed is 3x squared. But if you do it using this power rule, you'll get the same result either way. Okay, so now we have the square root of x. And so we know that the square root of x is x to the 1/2. And so the antiderivative, we've seen this one a couple times now, is going to have an exponent of 3/2 and then a coefficient of 2/3. And then our last part says plus sine of x. We have to think of what is a function that when you take its derivative, you get sine of x. So we know that the derivative of cosine is actually negative sine, right? So if I said plus cosine of x, that would actually be wrong, right? Because if you take the derivative of cosine, you would get negative sine, and here we have a plus. And so how do we deal with that? Well, we just say negative cosine. So the antiderivative of sine is negative cosine. And then we say plus c, because we're currently dealing with the most general antiderivative. So let me just write this a little bit clearer. I'm just going to simplify this part here. So we have 2e to the x minus x cubed plus 2/3 x to the 3/2 minus cosine of x plus c. Okay, so that's our general antiderivative. So now we have to use the fact that f of 0 is equal to 5. So one thing I just want to quickly point out is that if you were to just look at this and say, oh, f of 0 is equal to 5, and then assume that c was going to equal 5, that would actually be wrong. So we really do have to go through the motions of plugging in 0 for x and see what that gives us, because for some functions, it will be true that c ends up being whatever this number is, but that's not always true. It really depends on the type of function you're dealing with. So let's actually plug in 0 and see what we get. Oops. F of 0 is equal to 2 times e to the 0 minus 0 cubed plus 2/3 times 0 to the 3/2 minus cosine of 0 plus c. Okay, so what does this simplify to? Well, e to the 0 is 1, right? Any number to the 0 is 1, so e to the 0 is 1, and so we get 2. 0 cubed is 0, so this goes away. 0 to the 3/2 is 0, that goes away. Cosine of 0, that's 1, right? Cosine of 0 is, if you go on the unit circle and an angle of 0 and find the x coordinate, you get 1. And so cosine of 0 is 1. Okay, so now we know that f of 0 is equal to 1 plus c. And so now what we want to do is we want to take 1 plus c and set it equal to what we're told that f of 0 equals, right? We're told that f of 0 is 5. And so we can take this and set it equal to 5. And so now we can solve this for c, right? We can subtract 1 from both sides and we get c is 4. And so now we can put this back into our function, and that will give us our final answer. So our final answer is that our antiderivative is equal to 2 times e to the x minus x cubed plus 2/3 times x to the 3/2 minus cosine of x plus 4. So that's really all that is additional about this kind of finding a specific one. You're just given one little extra piece of information, and that enables you to figure out what c is. Okay, so next thing I want to look at is just an application of antiderivatives. So this is probably like the most kind of common application that you probably learned about derivatives in calculus is the relationship between a position function, a velocity function, and an acceleration function. So hopefully in your Calculus 1 class, you learned that if you take the derivative of a position function, you get a velocity function, right? Because derivative is about a rate of change. And if you're looking at the rate of change of position, well, that's what velocity means. And then if you look at how the velocity of is changing, right? That's about speeding up and slowing down. That gives you acceleration. So derivative of position is velocity, derivative of velocity is acceleration. And then working the other way, that will tell you something about antiderivatives, right? So if you take the antiderivative of acceleration, that is always going to give you the velocity. And if you take the antiderivative of velocity, that is going to give you a position function. And so this will enable us, just like how in Calculus 1, you probably did problems where you're given a position function and you find the velocity function. Now we can go the other direction. So you can be given a acceleration function and find the velocity function, and then find the position function from there. So let's try this out. So this says, on Earth, the acceleration due to gravity is negative 9.8 meters per second. Suppose you throw a ball into the air with an initial velocity of 4 meters per second. Find a function that gives the velocity of the ball after t seconds. So in this case, what are we really given here? We're given the acceleration function. right? We're told that the acceleration due to gravity is negative 9.8 meters per second squared. And so that means that the acceleration function is actually a constant function. It's just negative 9.8. So acceleration on Earth is always going to be negative 9.8 meters per second squared, acceleration due to gravity. Okay, so let's think about what other information is given here. So we're also told that the ball is thrown with an initial velocity of 4 meters per second. So what's another way of saying that? Well, that means that when t is equal to 0, the velocity is 4, right? And so we can write this as v of 0 is equal to 4. So what we're trying to find in this question is the velocity function, right? It says find a function that gives the velocity of the ball after t seconds. So in order to find the velocity function, we have to take the antiderivative of the acceleration function. So what would be the antiderivative of negative 9.8? Well, negative 9.8 is a constant, right? And so the antiderivative of a constant is just that constant times your variable. Right? If you take the derivative of negative 9.8 times t, you would get negative 9.8. So the antiderivative of negative 9.8 is negative 9.8 times t. And then we have plus c. And so the question is really to figure out what that plus c is. And so that's where the v of 0 is equal to 4 comes in, right? The extra information is given that the initial velocity is 4. And so if we plug in 0, we would get negative 9.8 times 0 plus c. And so that's just going to equal c, right? The first part is going to become 0. And so that tells us that because our initial velocity is supposed to equal 4, that tells us that c is equal to 4. So in this case, the initial, or the c actually is equal to that number that v of 0 was. And so this tells us that our velocity function is negative 9.8 t plus 4. So that is the function that gives the velocity of this ball after t seconds. Okay, so now that we have the velocity function, now we can find a function that gives the position of the ball. Right, so the position function is going to be the antiderivative of the velocity function. And again, we're given this extra information. We're told that the ball is thrown from a height of 2 meters. So what that tells us is that the initial height is 2 meters, right? And so in other words, oftentimes s of t is used as the position function. I don't know why, but that's just kind of a convention. So this means that s of 0 is equal to 2. Okay, so let's now use our velocity function to find the position function. So if our velocity function is negative 9.8 t plus 4, we have to find the antiderivative to find our position function. And so our position function is going to be negative 9.8 times, so the antiderivative of t would be 1/2 t squared. And then we have plus 4 times t, right? The antiderivative of 4 is 4 times t. And then we have plus c. So let's clean this up a little bit. So this is going to be equal to 1/2 of negative 9.8. What is that? That's negative 4.9. Okay, and so now we can use the fact that the position at 0 is supposed to be equal to 2. And so if we plug 0 into our function, we get negative 4.9 times 0 squared plus 4 times 0 plus c. And so again, that's just going to equal c, right? Because the other parts just turn to 0. And so we're left with c. And so in this case, c is just equal to 2, right? Because s of 0 is supposed to equal 2, so c is equal to 2. And so this tells us that our position function is negative 4.9 t squared plus 4t plus 2. So if you've taken any physics classes, you probably learned these different kind of formulas for the, like height of a projectile after a certain amount of time, or the velocity of a projectile after a certain amount of time. And now you can really see where those formulas come from. So they really are coming straight from the fact that the acceleration due to gravity is negative 9.8 meters per second squared. Just with that information, plus the information about the initial velocity, and then the initial position, we're actually able to figure out a formula for the height of the ball as a function of time. So the one last thing I want to look at is some examples of trickier antiderivatives. So these are some antiderivatives that we'll learn methods for finding later on in the class. But I think that just getting a little bit of a sense of how these more complicated antiderivatives work earlier on in the quarter will just help you feel a little bit more confident later on when we come back to these. So for these, what we're going to do is we're actually going to use guess and check. So maybe for the first example, follow along with me and watch what I do. But then the next two examples, I would really recommend that you pause and try them yourself, just so you can really get a sense of how this guess and check method works. Okay, so our first example is f of x is equal to cosine of negative x. So again, we're finding the antiderivative. So that means we're trying to figure out what would be the function that when you take its derivative, you get cosine of negative x. So what might be a guess that we could make here? So the first guess that I might have would be sine of negative x plus c. Right, so where am I coming up with this guess? Well, we know that the antiderivative of cosine is sine, right? The antiderivative of cosine of x is sine of x. And then, well, if we have negative x in our original function, we should still have negative x in the antiderivative. So let's see what happens if we actually check this, this antiderivative that we guessed. So what happens when we take the derivative of cosine of negative x? Well, remember that when you're taking the derivative of a function that looks like this, what's called a composite function, you have to use the chain rule. So if you don't really remember how the chain rule works, I would really recommend that you go back and study your Calculus 1, because it's going to be really essential that you understand and remember the chain rule for this class. So I'll actually link some videos that I made for Calculus 1 that you can go back and review if you want to review the chain rule. But yeah, so how does the chain rule work? Well, we take kind of the outside derivative first, right? We would say cosine of negative x. That's the first part of the chain rule, is that outside derivative. But then you have to multiply by the derivative of the inside function, right? And so what's our inside function in this case? Well, the inside function is negative x. And so what's the derivative of negative x? It's negative 1. And then the plus c, well, the derivative of that is just 0, right? So I'll just say plus 0. And so this would give us negative cosine of negative x. And that's not correct, right? That's not what we're looking for. We're trying to figure out what is the function that when you take its derivative, you get just cosine, not negative cosine, just cosine. And so what adjustment can we make to this function that would allow us to get rid of the negative sign? Well, if we were just to include a negative sign at the beginning, that would actually do it, right? So if we instead say f of x is equal to negative sine of negative x plus c, let's see how that one works out. So if we check this one, we would now have negative cosine of x, of negative x, right? Because the outside derivative is still going to be cosine of negative x, but we have this extra negative sign now. And then we multiply by the derivative of the inside function, which is negative 1, and then we have plus 0 from the c. And so this is now going to give us negative times negative, which is positive cosine of negative x, and that is correct. So, you know, this might not be the most satisfying method to you, right? You're like, well, how do you guess? Like, how are you coming up with these guesses? Again, further on in the quarter, we will learn a concrete method that will allow you to do this without guess and check. But I just think it's really valuable to be comfortable playing around. And as I said earlier in the video, one of the best things you can do to really understand Calculus 2 is find antiderivatives and then check them. Checking your work is just going to be so important to really understanding why antiderivatives work the way they do. And so that's really what we're doing here, right? We're guessing something that seems like it could be right, finding the derivative and realizing, okay, that's not quite right, and using what we found for our derivative to adjust the antiderivative and come up with the correct one. So this is our correct antiderivative. Okay, so now that you have a little bit of a taste of how guess and check works, I would recommend that you try this next one yourself. But you know, then I'll go over it as well so you can come back. Okay, so once again, we want to guess, right? We want to come up with something that seems like it could be the antiderivative. So we know that the antiderivative of e to the x is just e to the x, right? So you might guess that the antiderivative of e to the 3x is just e to the 3x, right? That seems like a reasonable assumption. But let's check what happens when you actually find the derivative of this. So what is the derivative of e to the 3x? Well, remember, you have to use the chain rule, right? So what would the derivative be? Well, the outside part of the derivative would just be e to the 3x. But then you have to multiply by the derivative of the exponent, right? And so this would be 3 times e to the 3x plus c. Or sorry, not plus c, plus 0. And that's not right, right? That doesn't match our original function. We want e to the 3x. We don't want 3 times e to the 3x. And so this did not work. Okay, this is a fail. But it helps us figure out what the actual antiderivative is, right? So how do we compensate for this 3? Well, we can multiply by 1/3. So what if we tried to make our original function 1/3 e to the 3x plus c? Let's see how that works. So if we check this one, now our derivative is going to be 1/3 times, and then the derivative of e to the 3x, well, we already did that, right? That was 3 times e to the 3x plus 0. And so when we simplify this, we have 1/3 times 3, and that's just e to the 3x. And that's exactly what we wanted. That's what we wanted our derivative to equal. And so again, it's this idea of kind of having to compensate for something, right? Like having to multiply by something extra in order to adjust for this extra stuff that's going on in the exponent. So in this case, it was multiplying by 1/3. In the previous example, it was multiplying by -1 because we had this negative sign on the inside. Okay, last example. This one's a little bit different. So this one is 2x times e to the x squared. So this one's a little bit different in that you'll see that the first guess we're going to make is actually going to be the correct guess. So this one you have to kind of just recognize how the chain rule works and see that the result we have here is actually the result of the chain rule. So again, how does the chain rule work? The chain rule works by you take kind of an outside derivative and then an inside derivative. And so what would be really important to note in this example is that we have this composite function, right? We have e to the x squared. And what happens when you take the derivative of x squared? Well, you actually get 2x. So when you have a function where you can see that the derivative of one part of the function is actually contained in the function as well, that's a hint that it is the result of the chain rule. So let's try to do the function as our original function, e to the x squared plus c, and we'll see what this comes out to be. So what would happen if we were to take the derivative of this? Well, we would use the chain rule, right? And so the chain rule would tell us to first do the outside part of the derivative, so e to the x squared, and then we would take the inside part of the derivative. So that would be the derivative of x squared. And so what's the derivative of x squared? It's 2x. And then we have plus c, which is the derivative of that is 0. And so altogether, we end up with 2x times e to the x squared, and that's exactly what we started with. And so that is our antiderivative. So again, this, I know this is tricky. I don't necessarily expect that you would recognize this, but I want you to start kind of looking for things like this. So looking for the fact that when you have one part of the function and then it's being multiplied with the derivative of that part of the function, that's kind of a hint that its antiderivative might be a function involving the chain rule. All right, so that is it for this video. In our next video, we're going to get into something that will seem initially like completely unrelated to this. Like I said at the beginning, we're going to be moving into some stuff that will feel different from this, but then we'll bring it back and see how it connects to antiderivatives. So I'll see you all in the next video.